So, we're not going to get all the way through this problem, but we're going to make it a substantial way there. And what it is another circuit analysis problem. In fact, this is you know, I'm doing two examples, and I'm going to bring in pretty much every alternative way, you know, alternative aspect of these problems, except for going up to a higher order differential equation. The same process applies. It just takes longer, so I didn't want to have to go another like 2 pages of in-class example. So this one's first order as well, but it hits all the other notes that you need. So and I can always fall back on the fact that differential equations is a prereq. So notice that we have yet to talk about alternating current AC circuit analysis or direct current DC circuit analysis. In fact, these ambiguous terms can mean a few different things. Approximately, an AC circuit analysis is one for which the input is sinusoidal, and a DC circuit analysis is one for which the input is a constant. This ignores transient response, which is early response when the initial condition response dominates, versus the steady state response, later response when initial condition response has decayed. So the transient response considerations we're ignoring in this little definition of AC versus DC circuit analysis. We're going to consider those two terms more in the next lecture. There's a lot to discuss, so that's why I split it off into a different lecture. But for now, we can just say we have remained general enough to be able to handle sinusoidal and constant sources in both transient and steady state response. So all of AC and DC circuit analysis is still packed into what we've done. We've never like made any assumptions about the type of input it is, or that it's in steady state versus transient response. We've never made any of those assumptions. So everything we're doing applies to all of these cases. The last example, which is in my notes at least showing up as a question mark, I hope it came through on yours, but the previous example that we just finished features a circuit with a constant voltage source and a capacitor. Okay, we didn't consider it in just steady state though. We considered the transient response, the total response, which includes transient and steady state. Now we consider transient and steady state response together, the total response of a circuit with a sinusoidal current source. So before it was a constant source, right? So the sinusoidal now. And now instead of being a voltage source, we have a current source, so we change that. And instead of having a capacitor in it, we have an inductor. Because why change one thing when you could change more? So, here we go. The example itself. RL circuit analysis with the sinusoidal force. Given the RL circuit shown, the current input, IS of t equals A sine omega t, and initial condition IL at time equals 0 is equal to some I0, which could be 5 amps or whatever, it doesn't matter. What are IL and VL for all time greater than or equal to 0? So that's the problem before us. Sounds a lot like some of the homework. Right? All right, so what is step 1? 6 steps. Draw the circuit. Oh, bam, bam, done. Step 2? Sign direction. Oh, they're already defined. Check. We're a third of the way done already. Okay, step 3.
Elemental equations.
Elemental equations. So we like to list off. So I'll write elemental. Elemental. All right. we have an inductor and we have a resistor. So for the inductor, what is the elemental equation? IL dt equals
L VL.
1 over L times VL. Yeah. Good. And for the resistor, what is our elemental equation?
VR equals IR times R.
Yeah. Excellent. So step 3 done. That means we're halfway already, and we've hardly used any paper. 4. Finding the KCL equations. And this is actually, this shows you a little bit of a weakness. Remember I told you that this systematic approach is like, it works most of the time, but you might have to like write an extra KCL equation or a KVL equation, or one less than the rules prescribe in a given situation. This is one of those cases. There are 2 nodes that don't contain, that are not connected to a voltage source, right? In this circuit. There's this node up here, and there's this node down here, which encompasses, of course, all of this wire, each node does. And we are to write Kirchhoff's current law, and our rules say that we need to do it for those 2 nodes. But notice that those 2 nodes are going to give exactly the same value. It's exactly the same equation, because say you took the top one, it's going to say everything going in is IS equals everything going out, which is IR plus IL. Down here, it would say, oh, everything going in, IR plus IL has to equal everything going out, which is IS, which is the same equation. So we only need one of them because they're the same. So we have IR plus IL equals IS. Okay. And that's why we'll eventually get a more systematic approach that will be able to handle this sort of situation without any ambiguity. But we can still work our way through without. I mean, like we notice, oh, 2 the same equation, no big deal. So it works. Most of the issues are pretty benign with this. So Kirchhoff's voltage law is step 5. And we need to sum the voltage around each loop. But the loop with the current source in it is excluded from that in the rule. We don't want to do that for loops with current sources. It's actually fine to do it, but you end up with an extra variable that we don't need. So you can solve for it still. It just tells you that what the voltage across the current source is, but you don't need it. So we just usually exclude that. We just use this loop, and that loop says what? About the voltage across the resistor and the voltage across the inductor.
VR minus VL should be 0.
Yeah. VR minus VL equals 0. And so VL equals VR, right? All right, we're already on step 6, so we're practically done. This is some algebra. It's actually not too bad. So just solve, right? We have our 4 equations, 4 unknowns. We want to get it down to a single, because we only have one time derivative here. So we want to get it down to one single first order ODE. And we're going to do that by eliminating 3 variables, right? They're going to be the voltage across the inductor, the voltage across the resistor, and the current through the resistor. And I'm going to, in step A, sorry. Step A is to rewrite our our two elemental equations while eliminating two of the variables here. And I'm going to choose to eliminate, so I'll actually write that. Let's eliminate, I'm going to choose to eliminate, I'll follow my notes for once. I'm going to choose to eliminate VL and IR. So you might say, okay, could you have chosen to eliminate, say, VL and VR? Yes, that would have been a fine choice. Could you have chosen to eliminate IR and VR? Yes. And actually, in fact, that would have been fine. But if you would have chosen to eliminate IL, which is one of the derivative ones, technically you can do it because it would just, when you substitute in for IL, you would get a differential equation and another variable, which is fine. But if you do, notice that, say you wanted to do it for IR, you would have to plug in this relationship here to find IR in terms of, or IL in terms of IR and IS. And when you plug that into this equation, you take the time derivative of an input, which is fine, you can do that, but it's just mucking around in things we don't want to do. So that's why I'm kind of guiding us towards leaving the time derivative variables alone and eliminating other stuff. So in the L equation, I'm going to leave the IL alone because there's a time derivative. DIL dt equals 1 over L. And I want to eliminate VL from this equation. So let's look up here. Oh, gee, that's really hard. We'll just plug in VR for it. Check. Got that one gone. Nice. Ooh, now let's do the other one. We want to eliminate IR. So we have VR equals IR times R, but we want to get rid of IR. This equation up here will let us do that, right? This KCL equation. It tells us that IR is equal to IS minus IL. So I just need to plug in IS minus IL, and it's times R, right? Good. So of the four equations that we had, we're down to 2. We want to get it down to 1 because there's only one with time derivative in it. So we need to eliminate, which variable should we eliminate in B? VR. Let's eliminate VR. And it's pretty easy to do. Because you can just use this R equation, it's already solved for VR, and plug it into the L equation. And we do that with, okay, DIL dt equals 1 over L times IS minus IL times R. Bring the R out front, and that gives us R over L IS minus IL. This is starting to look familiar, I bet. Kind of like some of the other problem we did. So similar. It's first order. All of them look the same. So let's do the same thing we did before and rewrite it in terms of the form that we're used to for a first order equation. And let's define a time constant again to be L over R. L over R. And that's because we need to multiply both sides by L over R to get that expression out here, and that's what our time constant is defined as. So this is our definition. That leaves us with tau DIL dt we want to add the IL over. So we get IL on one side. And it's equal to IS. Okay. Nice. So now we're ready for part C, where we just need to solve the ODE. So, part C. So we'll break that down, and we'll do step 1, homogeneous solution, right? We start with the characteristic equation. Which is tau times, oh, there's a time derivative, but it's only first order, so lambda, tau lambda plus 1, right? There's no time derivative on this one, so just plus 1 equals 0. Always equals 0. So this is exactly the same characteristic equation. Tau lambda plus 1 equals 0. It turns out for a first order equation, it's always this. I mean, lambda, tau changes, but lambda will always be equal to -1 over tau, which gives us the homogeneous solution as being IL homogeneous of T equals kappa e to the minus T over tau. So same homogeneous solution. It always turns out this way. You just got to know what tau is. And I actually don't mind if you guys start saying like, oh, this is a first order equation. The homogeneous solution is going to be this. Has to be. Now, I do, you still do need to solve for what lambda is in the other cases, in second order, third order, because you can have repeating roots, and that's where trouble
Sorry,
comes
what
in.
is kappa again?
Kappa is, sorry, I didn't say, it's just some constant.
Oh.
So we haven't defined it yet. So I know that we usually would use C, right, in that spot for the homogeneous solution, but since we use it for the capacitance, we are SOL. So we use kappa. Yeah. Cool. So now we're ready to do the particular solution, right? And I don't want to get ahead of the other section because we stopped here, but I want to, I'll discuss a little bit how we would go about doing this, right? So to find the particular solution, we're going to need to determine what the form of it should be based on the form of the input, which in this case is sinusoidal, right? A sine omega t. So the assumed form is actually going to be, I'll give you the little preview here, not V, IL particular T is equal to K1, I want to make sure I use the sine and cosine definitions the same. Okay, K1 sine omega t plus K2 cosine omega t. So our assumption is that the particular solution is going to be sinusoidal, and in fact this is a single sinusoid. It's at the same frequency, these two, with the phase offset. So if you add these two, that's equivalent to that. So our goal will be to plug this in to our differential equation, just like before. So our differential equation is this. So we plug this in, and then we have to solve for our undetermined coefficients again, right? Which in this time, instead of being just a single constant, we have two constants. And you might say, how are we going to get from one equation two constants? And I'll tell you the secret. We still have a minute left, so you still get another moment of secret. The secret is that you can set equal the cosine coefficients and the sine coefficients on each side. So on the left-hand side, you're going to end up with a bunch of sines and cosines on the left-hand side. On the right-hand side, you're going to have a sine and no cosine. The sine coefficients has to be equal on both sides, and the cosine coefficients has to be equal on both sides. That gives you two linear algebraic equations. The reason why you can find more information in it than you would expect out of one equation is that it's a nonlinear equation, because it's got sines and cosines in it. More info packed into it. So that's what we're going to do. We're going to solve and discover two things, of course. First thing we'll discover is what K1 and K2 are. And the second thing we'll discover is, OMG, there are solutions for K1 and K2. Therefore, our assumption that this was a particular solution is correct. And if we ever couldn't solve for K1 and K2, we would know that our assumption is incorrect, or that we just didn't succeed at solving.
I was gonna say. Okay, so it's just wrong.
That's another possibility. In this case, we would be wrong if we couldn't solve. That'll be in the lab, or I don't know how he's having you submit them. Maybe on Moodle. But yeah, not to me in person. How is that going? How are those reports going?